Two blocks A and B of mass 4 kilograms and 14 kilograms respectively are connected by a light string, so I don't have to worry about the mass of the string, on a smooth horizontal surface, so I don't have to worry about friction, when a force F is applied on block B. The acceleration of the blocks is 2.5 meters per second squared. Determine the tension and the magnitude of F. The first thing I do is I draw a force diagram for the 4 kilogram block, and there's only one force acting on it, that is tension. So force resultant on the 4 kilogram block is mass times acceleration. It's going horizontally. I can't say that acceleration is 9.8. Mass is 4, acceleration is 2.5. And I land up with 10 newtons. That's the first answer already done. The next one is 14 kilograms, and I have a horizontal applied force, and I have a tension acting backwards. This system is going to obviously move forward because this is the applied force and there is no friction. So there's nothing holding the system back at all. So it's obviously going to move to the right. So force resultant is equal to big minus small. Force resultant is mass times the acceleration of the system is equal to the big force that I don't know minus the small force, which is tension, and tension I've just worked out is 10. So you're going to go 14 times 2.5, and you're going to throw this 10 over to the other side and add it on, and you find that your force turns out to be 45 newtons. I've got a 25 kilogram block and I've got a 7 kilogram block. The first thing I need to think about is who wins. 25 kilograms is going to pull 7 kilograms over this pulley. They are connected by a string, and the string is placed over a frictionless pulley, which is good news. Assuming that the mass of the strings is negligible, good news as well, just determine, and we need to consider just the blocks. The first thing that's quite obvious and probably worth a mark is to say that T1 is equal to T2. That's our first piece of information. And then we are going to try and work out the force resultant on each block. I'm going to call this block, well, let's call it 25 kilograms, why don't we, and 7 kilograms. Let's think about what's happening on each one. There is a weight acting down of 25 times 9.8, and there's a weight acting down of 7 times the 9.8, and I land up with a tension acting up and a tension acting upwards. Okay, so we've got two forces on both blocks in the vertical direction. Force resultant is equal to the big force minus the small force, and remember, this whole system is moving around and down. So the big force is going to be my 25 times 9.8, in other words the weight, minus the tension. My force resultant is 25 multiplied by the acceleration of the system. So I've got 245 minus T1. Rearrange that, where T1 is equal to 245 minus 25A. Looking at the 7 kilogram block, force resultant is equal to the big force. And remember here, this is moving upwards, so the big force is going to be tension, minus the small force, which is going to be the weight, and that's 68.6. And force resultant is 7 times the acceleration of the system. Now notice the difference between the acceleration of the system and when I'm calculating weight. The system moves with a certain acceleration. Weight is only one part of the forces that are exerted on each of those blocks. and I land up with T2 minus 68, 6. Rearrange that, make T2 the subject, and I get 7a plus 68, 6. But we do know that T1 is equal to T2, so I can put these 245 minus 25a is equal to 7a plus 68, 6, and I find that a turns out to be 5,51 meters per second squared. And they're asking for the 25 kilogram block, so the 25 kilogram block is going downwards. Then they want to know what is the force, T2. So if I'm going to calculate T2, I'm going to go and I'm going to substitute this 5,51 back in for that 7a, and it turns out that T2 is going to be 109,375 when I substitute back in. And it's an upward force because T2 is going upwards. Now we have got two wooden crates of 15 and 5 kilograms. They're lying on a horizontal surface. No one said it was smooth. The blocks are pushed across the surface by a person applying a horizontal force to the 15 kilogram block. The frictional forces on the two blocks are as follows. So working against, I've got 9 newtons and 3 newtons. If during the motion the 5 kilogram block exerts a force of 20 newtons onto the 15 kilogram block, so 5 kilograms is exerting 20 newtons onto 15, which means that 15 is exerting 20 newtons back onto 5. I'm going to separate these two blocks out. 15 has got a force acting onto it from the front. And if you don't mind, I'm going to do it like a free body diagram. So I'm going to say that force actually pushes to the right of 15. And it is being pushed backwards by the 5 kilograms 20 Newton force. So that is a reaction force. This is an applied force. They haven't asked me to draw the diagrams, but that's what they are. I also have working against the motion a 9 Newton force of friction. If I take just the 5 kilogram block, I have got, pushing it towards the right, there's 20 newtons, which is the action force of the 15 kilogram onto the 5 kilogram. And working against it is a frictional force of 3 newtons. Let's look at force resultant. Force resultant is always mass times the acceleration of the system, which is not 9,8, is equal to the big force. Obviously, this whole system is moving to the right. We can only assume it's moving towards the right. And so we're going to say big force minus 9 minus 20. Force to the right, less the two forces to the left. Looking at the other block, 5a, acceleration of the system, not 9,8, is equal to big force, 20, pushing to the right, minus small force, left, 3, and I land up with 17. So 5a is equal to 17, and I can therefore work out what a is equal to, and it turns out to be 3,4 meters per second squared. I'm then in a position to take that a up into that equation over there and determine the force. So I land up with 15 times 3,4 plus 20 plus 9 equals F. I've just thrown those both over there, and I find that my force turns out to be equal to 80 newtons.